In this problem we're given two equations, two models, one which gives us the millions of employees working for state governments in the United States, and a second equation which gives us the average wage for each of these employees. Both are T years after 2000. So because they both share the same input, we don't have to be concerned about multiplying or dividing them, since they're with reference to the same point in time. So if I plug in 0 here and 0 here, I'm referring to the same year. So we want total wages paid. Okay, well, the easiest way to start here is to think about what the units are for each of these two functions. So this is wage for each of these employees. This is in millions of employees. So one of our outputs for for E is in million employees, and the second function is W, which is the dollars for each employee, or the wage for each employee, so dollars per employee. Now, if we look at the unit analysis, millions of employees times dollars per employee, it's like you're saying, yeah, I work for so many hours, and I multiply that by what I make in dollars per hour, I get a total. So in this case, employees will cancel out, and we'll be left with millions of dollars, which is exactly what we want. That's a total. So in this case, T of T, the function which gives us the total wages, will be a product of the outputs of the two functions. So it'll be W of T, or however you want to look at it, E of T times W of T. Or we can flip-flop the order if you want. Now in letter B, we want to find the derivative and evaluate it at an input of little t equals 9 and explain what this value means. So we first need the derivative, and in order to do that, we need the prime of each function. So if we call E of t, let that be our f in our product rule, because it's a product of functions, and W of t be g in our product rule, then we need to find f prime and g prime. So f prime is the derivative of our E of t, which is this guy here. And so if I multiply that do my power rule on that, I believe I get 0.093 t squared plus 0.9 t minus 1.33. Constant goes away. G prime, which is the derivative of my wages function, well, that's going to require me to use exponential rule. So a times b to the u. So we need u prime. Well, what's the derivative of the exponent? Since that's 0.033 times t, the derivative will just be 0.033. That's just a result of the power rule. Times the natural log of the base. Well, the base is e, so that's just going to be the natural log of e. Times a times b to the u. Well, my a in this case is the coefficient 36357. B is my e, and u is 0.033 t. And so if we multiply these out, ln e goes away, and we get something along the lines of 1199.821. I believe that's what it comes out to. E to the 0.033 t. And so now we put this all together in the product rule, and we get t prime of t is equal to f prime g, which is 0.093 t squared. Probably separate this out a little bit, make it a little bit more visually simple to see. 0.9 t minus 1.33, that's f prime, times my g, which is my original w function, 36357 e to the 0.033 t, plus fg prime, which is e to the t, or e of t, excuse me, negative 0.031 t cubed, plus 0.45 t squared minus 1.33 t plus 65.28. Okay, well now the challenge is going to be and times my, g prime, which is 1199.821 e to the 0.033 t. So now that the challenge is often figuring out what this all evaluates to. So when we enter this in our calculator, we have to be fairly careful. We have to be careful for a couple of reasons. One, because it's really easy to try to plug something into an equation that's this size and get something that looks totally bizarre or just doesn't seem like a reasonable answer. And number two, it's very likely that we could just add in an extra parenthesis and get the wrong answer that way. So we'll just focus on working on the parentheses and all that stuff. So we want to evaluate t prime of 9. So we want to take this prime function, plug in 9, and see what we get. So we're just going to enter it in the way we see it, except I'm not going to put any parentheses where I absolutely don't need them, like 0.093 times t, which is 9 squared. I'll just write it like that. My calculator knows order of operations, so this won't be a problem. 0.9 times 9, minus 1.33. So minus 1.33. Close parenthesis. Now I'm going to open a parenthesis for the second piece here. This is G. 36357 second E. Now it opens up its own parenthesis because the whole power needs to be in parentheses. Otherwise, if I just do 0.033 times 9 and no parenthesis, then it'll raise it to 0.033 power and then multiply that whole result by 9. So I want to make sure that it does the multiplication first, and so I'll do it in parentheses. Now I'll close the parenthesis for that sucker, for the 36357. I'll add to that, this should be, I think I forgot a negative here. Yeah, let me back up here real quick. I'm going to put a negative for this guy. So second insert, I'll insert a negative. And now I'll start working on the second set of parentheses, negative 0.031 times 9 cubed. Plus 0.45 times 9 squared minus 1.33 times 9 plus 65.28. Close parenthesis. And now I'll do open parenthesis and do my 1199.821 times E raised to the 0.033 times 9. Close that parenthesis, close my exponential function parenthesis, and I believe that's it, so I should be able to hit enter now, and here's what I get. I get, it's about 71113. 71113. Now if you're slightly off, I think I might have, I think I probably missed something here, but this is pretty close. So 4 is what it should be. And maybe I just misevaluated 0.033 times 36357. Let's see how I did. 1199.781. Okay, so I was close, but that's close enough. So 71114 is our answer. So now interpretation, well, this is in, so we got to go back to think about what T of t represents. This is in millions of dollars. Little t represents years. So T prime of t, its outputs will be in millions of dollars per year. That's remember, derivative is a slope, so I need the units of the slope, millions of dollars per year. Okay, well, so that means that in what year? Well, it was in t equals 9, so in 2009, the total wages of state government, I'll just abbreviate that, employees was increasing by $71114 million per year. And that's it. We're done.